In this video, I'm going to be showing you guys how you can design the layout of a CMOS NOT gate using Cadence Virtuoso. So for this tutorial, I'm going to be sticking up with a 90 nanometer technology using the Layout Excel tool. So I'm going to simply go to terminal and I'm going to invoke the tool. So here we have the tool. I'm going to simply open up my existing project for schematic for the CMOS inverter. So this is my CMOS inverter. So I'm going to open up the schematic, simply hit OK. So as you can see, this is my schematic for CMOS inverter, and I've sized the transistors as well. And as you can see, we got the inversion voltage at 415 nanometers, which is there in my previous tutorial. So now what I'm going to do, I'm going to simply create a copy of this file, the schematic, and let me just name it as not underscore lay. Okay, then I'm going to open that copy which we just created, not underscore lay. Okay, now you have to basically remove this VDD, because Cadence does not accept this VDD once it is there in the schematic. So for the layout part, it accepts only these pins. So you have to replace this VDD with the VDD pin, and that's it. For instance, if you have two inputs to the transistors which take this in pin, like for instance, if this guy has the in pin and this guy in some other network also has the in pin as the input, so you have to name this the second guy as the wire connecting to the second guy as a label, not the pin separately for the second transistor. So yeah, that's it. And then you have to go to launch, Layout Excel, create new. Okay, oh, I'm sorry, wait, first you have to go to this PMOS, then you have to edit the properties. Then you have to you set the body tie to detached, right tab, because we want it at the right side, apply. And for the NMOS, we have to go to again body type, detached, left tab, apply. Okay, now check and save, launch, Layout Excel, create new, again configuration, create new. Okay, and here we have, this is the Layout Excel tool from Cadence, and here we are going to open the display settings, and we are going to you guys just follow the configuration which I'm setting over here. This is 0.005 and this guy is 0.005. This is basically the way you want to display your schematic, your layout, and that's it. Okay, where the heck is that guy? Okay, so now you have to go to DRG edit and hit notify over here and press apply. You might get one more option here, three tick options. You have 3 check boxes. You have to basically set notify over there as well, then apply. Okay, then you have to go to connectivity, then generate all from source, then snap boundary, the minimum separation is 0.12 in boundary, instances should be chained, then IO pins are the pins connecting your schematic the outside world. It should be metal 1 drawing, apply, PR boundary. Okay, everything else is okay. You have to simply hit OK. Now here it is, your IO pins are basically in metal 1 configuration, all of them, and you have the body terminal detached, and here you have the body terminal detached as well. So now what you have to do, you have to basically align this poly, this green colored is the poly, to the poly below. So simply first you have to basically remove this box over here, keep it somewhere else in the sheet, because once you do something wrong over here and you are obviously going to delete it, you might delete this box as well. And trust me, bringing this box back is very difficult. So you have to select this. First select everything. Go to edit, hierarchy, flatten, flat cells, preserve cells, everything. Just select everything. Okay, that's it. Then select this part over here, then press M on your keyboard, then click once and just simply align the poly of the pull up network to the pull down network, and boom, that's it. And I also suggest I'm going to give you a good suggestion over here. Just move this whole thing in between so that you get it aligned in the schematic, in the area, sorry. Yeah, now we have to connect the paths. So simply select the type of path you want. Like we want to connect this poly to this poly, we will simply highlight poly over here and press P on the keyboard, and that's it. I'm sorry, bring it from here, double click, and here you have just made your poly. Then you have to, yeah, now we have to go to this part, this metal pin over here. Then you have to select the metal layer. Then we have to basically align this like this and we have to basically make a metal path over here, so that all our connections from the contacts from the upper the pull up network are going to be connected. So this guy over here is the, let us consider it as the source for the PMOS, this part over here. So what I'm going to do, I'm going to simply connect this source to the VDD. But before knowing this, you should be familiar with the concept of stick diagram. Now anyways, you can watch any YouTube tutorial or your professor, whatever your professor has taught you. But yeah, that's how the idea is. That's the, those are the basics to design the layout. And now you have to basically do the same thing to the ground as well. Oops. Make sure you align this guy inside this path. And we have just made the two terminals. Now the VDD is this guy. This guy is giving power to this source of the PMOS. Then we have this gate. Then this is the drain. Now obviously drain is to be connected to this, and this guy is to be connected to this, and this guy as well. These two are the body terminals. And now what you have to do, as you know that the gate of both the NMOS and PMOS is connected to the input in CMOS inverter. So what we are going to do, we are going to select poly, and we are going to extend, yeah, we're going to extend this path. That's it. And we are going to go to create via, just hide this, and that's it. And we have to basically connect this contact to this pin by a metal path. That's it. So we have given the input. We will take the output now. Simply you have to connect this guy over here. Wait, can we connect it like this? Let me try it like this. I haven't tried it. Because this is going to be much easier, because there's less space over this region. Has might affect the adjacent metal layer, might affect the initial metal layer with which we are working. So now we have to connect these two guys. Then we have to connect this body terminal to the VDD. So yeah, our layout is pretty much made. So now we will obviously get one error for this body because we haven't sized the body, and yeah, it's saying something right now. What do you want, dude? Okay, let me just run the DRC. DRC will tell us everything. Go to Asura and run DRC. You have to select the DRC rule file from the GPDK90 library. I'm using the version 4.6. Okay, and you have to wait now. Yes, I want to view the results. Here is what we have done wrong. Okay, this guy is wrong. Okay, I got it. And this guy is wrong. Yeah, 2 errors, minimum 2 errors you will get. That's it. Now this guy is saying that the area of the N implantation and P implantation for the body terminal should be 0.15 micrometer. So let me just check what is the area for this body implantation. So apparently it is if you hit K on your keyboard, you get into the ruler mode. This is 0.29 by 0.28. I need to get my scientific calculator, which I never use. Where the heck is that thing? Oh, I have my phone. Yeah. So that's 0.28 micrometer multiplied by 0.29, which is equivalent to 0.0812 micrometers square, but the required area is 0.15 micrometer. So what we have to do, we will keep the length of this body constant, but we will basically increase the width. So assuming that the length is constant and we want the area as 0.15 micrometer square, we are going to divide 0.15 by 0.28, and by that simple mathematical logic, we are getting 0.5357 micrometers as the width of this particular configuration. So let us take another ruler config, ruler, whatever you call this. and we are going to extend this ruler to 0.54. Yeah, and also this is zero point 0.1 micrometer precisely. Yeah, all these rules are written in your, whoever has taught you VLSI system design, he must have mentioned all these design rules, so you should refer your notes. So yeah, now you have to extend this box over here and this box, which is the implantation box, to the required limits. So for that, what we are going to do, we are going to select this box, press S, and select, oops, oh, it's not extending, that's weird. Anyways, we can edit the properties of the box. We can use brute force. Rather than keeping the width 0.29, we can make it 0.54. And yeah, as you can see, it extended it in the other way. So yeah, we got 0.54, and same we have to do with this guy as well. So this guy is to be extended 0.1 micrometer from this guy. So this is precisely where we have to keep this box. Now initially we have to use a little bit of mathematics over here. It is 0.45, 1.45 micrometer, so we have to extend it 0.25. so we have to make its width as 1.45 plus 0.25, 1.7 micrometer. So yeah, this 1.45 should be 1.7 per supply. Okay, yep, that's it. This is precisely what you have to do. Now I suggest running DRC once more in order to ensure that you have rectified the sizing of the body terminal. And yes, now you have to do the same with the P body as well. So go to this P body, then you have to measure it. Oops, what is this? Something happened. Whoa, what the heck is this K? Alright, so now press K over here. Initially this body is let me just zoom it a little bit. Yeah, 0.28, but the length is 0.4555. Oops. Trust me, this tool is industry leading. Oh my god, no. I want to do this. Why don't I start from here? Finally. 0.455 by 0.455 by 0.28. Yeah, it's 28. Come on, Cadence. 0.28 multiplied by 0.455, it's 0.1274, which is less than 0.15. So now we will keep the the width. We'll keep the length constant, but we can increase the width. So what we will do is, we are assuming the length constant. Simply divide 0.15 by 0.28, and it should be 0.54 again. But I'm sorry, I did the other way around. You have to divide 0.15 by 0.28. 0.4455. Yeah. Now the width should be equivalent to 0.29. Let's assume it 0.28. Now you have to stretch this box by 0.28. Oh my god. 0.28. 0.28. Yeah, this much. You have to extend this by this much. Then again you have to keep the spacing between this line, the P implantation, and the outer box as 0.1 micrometer. So now for this, the initial length for this box was 0.28, and we are going to change it to 0.3. I'm sorry, 0.33. It's 0.33, not 0.28 or whatever I said. Apply. I'm just using maths, guys. It's nothing. It's literally nothing. Whatever the TRC rule is showing me, I'm just trying to make. 1 minute. No DRC. Now we will run LVS. Oh, there's one error. No DRC. So we have matched the schematic with the layout, and that's it. You have just designed your own NOT gate.